Our next speaker is Gavin Schmidt. He's the director of the NASA Goddard Institute for Space Studies and the principal investigator for its Model E Earth system model. And he was previously a senior climate advisor to the NASA administrator. He is a fellow of the American Geophysical Union and its inaugural recipient of the Climate Communication Prize. And today he's going to tell us about the challenges and potential of machine learning in climate modeling. Gavin, please.
Thank you very much. I can't really compete with the vast scope of the previous talk, so I'm just going to focus on climate modeling, and I'm going to try and tell you about why some of those approaches are not going to be helpful, but also try and point out where there are going to be useful things that we can do in the relatively short term. So here's my outline if you don't want to pay any more attention to me. System models are skillful, they are improving all the time, and they are useful representations of the climate. There's many issues at the level of fundamental processes, inclusion of things that we're not including, and the small scale interactions that occur. You can kind of deal with the issues with climate models is that they have biases, they are limited in scope, and they are limited in usability. And so all those three things are really the targets for any new approach to looking at climate. Machine learning has the potential to improve all of those things, but it does not supplant climate models. And I'll try and explain why you're never going to have a machine learned, data-driven model of climate change. Okay. And we are starting to see some useful applications. Okay, so that's basically my talk. You can leave now if you want to. Okay, this is where we started, right? I just want to point out that we have been doing this for an awfully long time, since the very first computer models, first computer architectures. This is a picture of a punch card. Some of you might remember these things. It's actually a line of code from our climate model back in the late 1970s. We have come a long way, but we're still using Fortran, which is kind of disappointing that ChatGPT didn't point out that it could code in Fortran if it can. But it should be higher profile. But anyway, moving on. So model predictions have been quite skillful. Like going back to the 1980s, here's what was projected using a very simple model, and this is the temperature that we've seen. This is the global mean temperatures. The first real GCM prediction of transient change was by Jim Hansen, whose job I now have. That was built in 1984 and has skillfully predicted the climate out to 2022. We've been doing better with climate models. This is generation of climate models that were built in the 2000s, early 2000s. They've done quite well, and we keep doing this, and this is the version that was done in 2005, and we've just done a new version which we can't really rate yet in terms of its projections because we haven't had enough time. Okay, climate modeling has been a process of assimilation. So I use this analogy with younger audiences, and they have no idea what I'm talking about. But anyway, but all of you remember the Borg, right? We will assimilate you. And so climate science has been a process of assimilation of lots of different other fields, right? It started off with meteorology and oceanography and cryosphere sciences, but has incorporated biology, ecosystems, ice sheet dynamics, vegetation, marine ecosystems, and all of these things are now what are usefully called Earth system models, right? And this has come to define the field. All these people in the 1980s were not climate scientists, but now they all are, right? So the field itself has assimilated other fields, and so now it's a much bigger and richer description than it was in the 1960s. And every so often we benchmarked these models, and these acronyms here, CMIP for 1, 2, 3, 4, 5. So there wasn't a CMIP 4, don't ask me about why. A couple model into comparison projects, and I put this down there because I'll come back to what they've done and how things have changed subsequently later on. Okay, so skill is improving, right? So this is a totally arbitrary measure. These are a bunch of models from each of those 3 generations. You know, a line out here is very bad. A line over there is much better. And you can see on average, the skill is getting better. So it's moving, the error is less as you go through time. And there's a range of skill across models. Now, one of the interesting things about these models is that if I took a different metric of how skillful they were, the ranking of the models would change, but the patterns of change are constant. Right, so there isn't one model that is the best model, but the collective skill of each of the generations of model has actually been improving across the board. Even for things that we haven't really been targeting, I'll give you here's an example. This a pointer? No. Okay. I'll give you an example here. So patterns of correlation to El Nino events. So El Nino events, big oscillations in the tropical Pacific. They have large teleconnections to rainfall in the American Southwest, drought in Indonesia, et cetera, et cetera. The skill with which the models predict what the consequences of an El Nino would be have been improving by generation, even though that this is a very kind of emergent property and it's not something that's targeted as part of the model development process, right? So the models are getting better across the board, even for difficult metrics. Okay, but what's wrong with climate models? Okay, I have a list. So systematic biases, right? So we know, for instance, that the models in this last generation have a broader range of climate sensitivity than we can understand from the real world. So the real world observations tell us that climate sensitivity is somewhere between 2.5 degrees and 4 degrees. That's the amount of warming that you would expect for a doubling of carbon dioxide in the atmosphere. And in the last generation of models, that kind of sensitivity goes from 1.8 to almost 6 degrees. Right, much broader than we actually understand. So the models are wrong as a collective in that sense. There are regional and local changes that are biased because the models don't include sufficient detail with the size of the mountains, the shape of the continents, and exactly where the Gulf Stream separates from the North American continent. These are due to resolution, right? You can't include as much detail as you want. Incompleteness, there are processes that we know that are happening that are not included in the models. And structural error, right? So because we're having to approximate many of the things that we're not explicitly calculating, it may well be that we have the physics, the phenomenology wrong, right? So all of those things are relevant. The other thing that we need to think about is scenario scope. So we're trying to predict things for the future. And obviously, the number of potential futures that we can look at is very finite. In fact, it's 4 different scenarios. And obviously, the scope of what could happen in the future is much, much broader than we are currently calculating, right? So 4 what are called socio-economic pathways do not span all of the possibilities. And we lack the ability to do on a routine basis things that would actually help policymakers. So policymaker says, oh, what would happen if we boost electric vehicles or we build a high-speed rail network? What impact would that have on the climate, on air quality? And we don't do that sufficiently. And perhaps more importantly, we fail on translatability. Like, how do you go from petabytes and petabytes of climate model output to an actual useful decision that anybody might make, right? It's very unclear how one should do that, and the degree to which these projections are usable is very much in question. And of course, the bottom line underneath all of these things is the models are too slow, right? So you talked about a month to do a training thing. Okay, these model runs on similar kinds of architecture will take 3 months, 6 months, over a year sometimes to run these simulations. So they are extremely expensive relative to what you want to get out of them. Okay, so here's an example of kind of what's kind of going wrong right now. This is, I think, okay, so this is the ECS is the climate sensitivity. The blue dots were the range of climate sensitivity in CMIT 5, right? So like 10 years ago, and the range of climate sensitivity in CMIT 6 has expanded. Okay, so one might have naively thought that as we get better computers and do more things, we would converge on the right answer. But what it actually has happened is that it has uncovered, as we put in more details, there's uncovered more uncertainties that we had not actually been addressing previously. And so there are true uncertainties. Most of these are associated with cloud microphysics, aerosol cloud interactions, very, very small scale issues, and they have caused the model spread to go beyond what we can, what we trust. And it's mostly clouds. And there's also a lot of aerosol things. You don't need to look too much at the details here, but these are different aerosol models. They have different amounts of sea salt. They have different amounts of sulfate. We are unable to tell you which one of these models is correct, or even closer to the real world, because we do not have observations of aerosol composition on a 3D basis around the world over time. And so we still have some very large uncertainties that are due to a lack of observations in the real world that we can't compute our way out of. Models are incomplete. This is an estimate of all the different things that are going on with sea level. You might think that sea level was a big deal for climate models, but it turns out that half of these elements are not actually included in most climate models. So they don't have any mountain glaciers because the mountains are not tall enough in the models. They don't have any dynamic changes in Greenland. They don't have any dynamic changes in Antarctica. And that's like 90% of what's going on in the, well, not quite, maybe 60% of what's going on in sea level. And we can't do that, right? So, we have some real issues with completeness even in those bigger simulated Earth system models. And it matters, right? So we can see that Antarctica is losing about 150 million metric tons of water every year. This comes from gravity measurements. So we're actually measuring how much mass there is on the continent. It's an incredible measurement, but you know, Greenland is losing even more mass, and the patterns that you see there, the red is where you're losing mass. So all around the edge of Greenland and in West Antarctica and around some of the other ice sheet systems in Antarctica, this is contributing about half of the sea level rise that we're seeing right now. It matters, and these are not included in any of the CM6 models, right? The impacts of this fresh water are not included in any of the models, right? The changes underneath the shelves that are actually driving the melting of the Thwaites Glacier and the Pine Island Glacier are not included in the models, okay? So, what does the model development cycle look like? Okay, you start off with the inputs, you know, the shape of the continents, the height of the mountains, what the vegetation looks like. We develop parameterizations for the things that we cannot do a priori. So obviously we have conservation of energy, mass, we have Navier-Stokes, those are great things. We have radio transfer, all of these things are very good. But there's a lot of things that we have to parameterize that are associated with small scale processes that are unresolved. And that can be cloud formation, rain formation, convection, but also you know, cloud, you know, microscale cloud aerosol interactions and the like. We have, because these are approximations, we have further degrees of freedom that we can play with to tune the model on an emergent basis. And we are using machine learning to do that because you end up with a very large parameter space. So in our current things, we have about a 45 dimensional parameter space that we sample very sparsely. We use a machine learning model to fill in the gaps, and then where the machine learning model tells us that something interesting is going on, or where we can expect to see more accurate model tuning, is where we go in and we find individual models or individual parameter sets that give us skillful models. We evaluate those models. We always find errors, and so we go back around and around and around, which is great for my career prospects, not so great for the rest of the world. Okay, so as you're all aware, there's a large spectrum of machine learning approaches that one can use that go from just tuning of physics-based code all the way to totally unstructured deep learning, with no physics. The key thing about predicting things into the future, it turns out, is physics. So purely data-driven learning of climate, we do not have enough data of different climate states to allow that to be useful. The data that we have that's of any use is effectively just the last 40 years or so, and there has not been sufficient climate change over that period for that to serve as a training data set for climate. And so all predictions of climate have to be physics-based. Now, it could be physics enhanced by machine learning in many different ways, but it has to be physics-based. We are trying to do that using approaches based on perturbed physics parameters. So you take the model as it is, you play around with the parameters, you select the parameters based on both an emulator and machine learning, and you try and get a diverse set of models that are equally good in some sense, but that have different emergent properties, such as their climate sensitivity. We could try and do that manually, effectively. You sample parameters, you run the model, you compare the observations, and you keep on going. But that's too slow. And so we are using a model surrogate for that, that allows us to kind of short circuit some of those connections with much lower computational cost. And that's actually quite successful. And this gives you, for instance, here's a whole suite of different model parameters that are kind of specific to a particular model, doesn't generalize perfectly. There are some observational metrics, there's about 35 observational metrics, 40 some parameters, and then we can calculate how any one of those parameters influences the skill in matching the observational metric. Now, this works quite well for atmospheric models, right? So atmospheric models, if you give them the sea surface temperature, the ocean temperatures, the sea ice distribution and things, they can't really go that far wrong, right? So you play around with a whole bunch of different things, and you can see which ones have an energy balance that's reasonable, have a cloud cover that's reasonable, et cetera, et cetera. When you start doing that in a coupled system where it's much freer to find its own path, this doesn't work at all. You end up not being able to sample space densely enough to even find one single place where the model will be successful. But it does help as you improve the physics, and then as you improve the tuning, you can end up with very nice improvements. So up at the top here, E2.1 minus the observations, you can see two very big red spots just off the coast of South America and Africa. That is due to the lack of marine stratus clouds in these simulations. Right, these are the low-level clouds that you see if you've ever been to San Francisco. It's the marine stratus fog cloud layers. And if you go to the next version of the model, those red dots are gone. Yay! And that's a combination of improving the resolution, improving the physics, and then calibrating that to match better the observations from satellite. And so we can make large improvements in model skill using a combination of physics and machine learning to guide the parameterization tuning. But if you don't have the right physics, you can't tune to the right physics, right? So here's some experimental work we're doing where you take a cloud scheme that is not very good, effectively, and you try and calculate what it's supposed to be doing, and this is the attempt of the machine learning to match that data, and it's not very good, right? It's like the data is very broad, and it's kind of wrong, and the power law based parameterization doesn't really capture what's going on. But if you change the physics so that it's actually more robust, you can actually end up with something that's much better and therefore more tunable to a machine learning model, right? So machine learning cannot get past the fact that your physics is incomplete or wrong, right? It can't fix that. And so you're going to have consistent and persistent biases where the physics is not appropriate. Let me just skip that. Okay, so where are things going right now? And I want to give you a sense of the challenge that we have. Right, so obviously we are going to higher resolution and greater complexity, right? So that's been the thrust of modeling over this entire time period. All of these things take more time, more effort. Give you a sense, if you double the resolution of a climate model, it's an order of magnitude longer to run, right? So currently, the CM6 models had resolutions of about 50 to 25 kilometers at best. To get to the point where you're resolving, mesoscale organization in convection clouds, you need to be there around 4 kilometers, 1 kilometer. That's an order of 5 doublings, and so that's 10,000 times. 10,000 to 100,000 times more compute in order to be able to do that. So we're not going to be there anytime soon. Machine learning can help. It can help with the downscaling. It can help with the parameterizations. It can help with the tuning. And I'll give you an example of where it can help with filling out some of the scope as well. I think those are very strong and important things we could be doing. But we also have to remember that we have to sample the true uncertainty. Right now, we have uncertainty because of the weather. We have uncertainty because of the driving factors that includes aerosols, the sun, volcanoes, greenhouse gases, and we have to have a sampling of the uncertainty due to the fact that we don't know the physics. Right, so we need to perturb the physics in such a way that we can get a full spread of the true uncertainty. And of course, none of that works unless we have better observational constraints. Right, so what we saw with CMIP6 was that as we put in more detail, the model started to diverge. Right now, that's because the physics got ahead of the observations, and so unless the observations can keep up, we're going to have continuing spread of uncertainty, and it needs to be constrained back down to what we think is most likely. So here are some scenarios. These are just done with the GIF model, but it's the same thing for most other models. Here's the real world. Here's the historical runs going up to 2022, and then these are the scenarios that we were asked to do. Right, but obviously there are more than 4 scenarios. Right, that we could be looking at. The scenarios that we used were designed in 2010, 2011. They don't include the impacts of COVID. They don't include any technological changes that we've really had, and so they're already obsolete, right? So I can guarantee, if somebody says, "Oh, which one of these pathways do you think we're on?" The answer is none of them. The real world is not going to look like this, except in some very broad sense. All right, and these go from SSP 585 is effectively like burn it all. But literally burn it all. And SSP 126 is stop burning it pretty much now. And so you might imagine that in the global mean we'll end up somewhere in between these things. But this is not useful for somebody who's trying to decide on, how big a seawall I should build, or how much water retention capacity do I need in this new drought environment that we find ourselves in, etc. Right? So these things are not sufficient. But we can, and this is great work by Watson Paris et al. We can train the models to produce spatial patterns from the scenarios that we have, and then run emulators to fill in some of those gaps as a function of different assumptions about greenhouse gases and aerosols and the like. And this works quite well, and I think can easily be extended to higher order weather statistics that will be more useful for people who are using these scenarios for adaptation planning. Can we improve how we use that multi-model ensemble? I mentioned that that some of those models have a larger spread in sensitivity than we can constrain. Well, we can constrain that, right? Let's throw out the models that have too much climate sensitivity, which includes the DOE model and the NCAR model and the UK Met Office model, which is kind of embarrassing. But we can do that. We can make constrained projections. But can we do better? Can we continually update a weighting of all the multi-models, the multi-model ensemble, as a function of new information as it comes in, right? So I think we can do that, and we can get kind of projections that are, as consistent with all the information that we have today, as a function of time going forward, instead of just thinking of it as a static projection that was just made once and then never changes. Can we do a better job with climate impact diagnostics? Now, the big problem that we have is that we're quite good at modeling what the global mean temperature is, but there are no decisions that actually depend on the global mean temperature, right? So if I'm a local planner and I care about sea level rise, it's connected to global mean temperatures, but it goes through 1,000 different pathways to get to the point where I have to make a decision about how high my seawall is, right? Can we make machine learning models give you a better estimate of exactly those diagnostics that you actually care about? And the problem is that everybody who has an application or everybody who runs a system has a different set of metrics, right? The person that cares about water resources or urban planning or public health or coastal defenses, they all have different metrics. And you would like to be able to co-produce with all of those people a selected set of predictions that was informed, that was appropriate, and you can't, right? Because there's far too many of them, and there's only a few people who know what they're talking about when it comes to the models, relatively speaking. So we have to tackle this question of scale. How do you scale the co-production of useful information? And there, I think there are some links between what one could do with these large language models that could generate query-specific code that could be applied to the databases that could help people in a much more rapid and useful way to get answers to their questions in a way that kind of cuts out the middle person, if that's possible. And these kinds of things, you can see that we have enough information to do the training, we have enough information to do independent evaluation, and so we can tell how useful these metrics and these outputs will be. And of course, if you're going to make $1 million, billion-dollar decisions on the basis of climate models, you need to have some trust in the process, right? You need to trust that all of the uncertainties have been included, and that this is useful information and it has some skill at predicting what's going on. We need to be able to demonstrate that for users in ways that we have not been able to do so far. One of the things that we really need to do is really have a national level investments in data analytics. And so that might be something that we can all get around. Destiny is this project in Europe that's been semi-funded so far. It's Destination Earth. There's a lot of different aspects to that, some of which are tractable, some of which are rather fanciful. But one of the things that they want to do is they want to build this data lake where all of these things really need to be in it, but basically where you have the atmospheric data, the modeling data, the weather data, the socioeconomic data, all on top of each other, so that you can actually really analyze these things properly. Right now, in the US, all of these things are very diversely put around, and you can't really tackle these things, except kind of in the cloud, but even in the cloud, not all of this data is there. So we need something that is much bigger and more appropriate for these kinds of things. So people have started talking about digital twins for climate. I'm almost done. And I put a question there because you know, the models that we've been building for 40 years are in effect digital twins of climate, right? So, but people are talking about something else. So, well, can we use machine learning, massive data, and all the Internet of Things to make better climate predictions? And I think the answer is no. So can you make better, higher resolution weather forecasts using more information and more data and crunching it in real time? The answer is yes, you can. Yes. So that is a tractable goal. And so the biggest part of Destiny is to do this, right? So that's fine. We should be doing that. There's an enormous amount of untapped data that could be incorporated into these models that is not currently being done. That can be done. There are some vague hints that this will give us better decadal climate predictability that are just all vaporware, as far as I can tell. There's no path from high resolution weather forecasts to better decadal predictability, because the processes underlying decadal predictability are totally different from the processes underlying a weather forecast. There is a goal here to improve integration with impact models. I talked a little bit about that just now. That is a very challenging task, though it is one that is necessary. And so that's a good thing to be trying to do, but we're a long way from that. Can you make better data visualizations of what's going on? Yes, of course, that's relatively easy. And can you improve interactive user engagement with models? I gave you an example of perhaps how we could do that, but that's still very much an open question. Let me make it clear that improving the skill and usability of climate projections is a very important goal, right? But multi-decadal climate predictions are a boundary value problem. Right? So some of you are physics people here, you know the difference between an initial value problem where you start off and you just keep on going until you get your answer, versus a boundary value problem where you shift the whole thing and you're looking at the changes in statistics as you go on. Decadal predictions are a boundary value problem, and we do not have sufficient changes in boundaries and changes in climate to train models directly on that. And so we have to rely on the most generalizable things that we have, which is physics, not improvements in initial forecasts do not improve boundary value problem skill necessarily. There are some things that you can do, but there's no general translatability there. There's no clear resolution, no clear relationship between things like the amount of detail you include in the model and its climate sensitivity. Right? In fact, there's no relationship at all, as far as we can tell, until perhaps you get down to the micro scale, which we are centuries away from. Right? But we can reduce the systematic biases through machine learning driven calibrations, training on physics-based models, and through changes in outputs. I think our biggest goal and our biggest possibility for success in the short term is improving usability based on better analytics, better downscaling, and tighter connections between the model outputs and the things that people actually need. So let me conclude, which is kind of where I started. Earth system models are skillful. They are increasingly skillful. They are useful. They are making useful predictions, but they have many issues. These issues range from fundamental things associated with clouds or cloud microphysics or ocean eddies, and they are missing still some important interactions that are key for understanding some of the things that we're already seeing happen in the Earth system. bias, scope, usability are the three main tasks where we can think about doing something. Machine learning has the ability and the potential to improve all three of those things, but it will not supplant the physics-based work that the system models. And we're starting to see some useful stuff. So I gave a talk a little bit like this maybe 2 years ago, and I was looking over it, and I changed like a few things, but the biggest thing that I changed is that last line, right? The last line previously was, yeah, I'm not seeing any useful applications, and now I think we're starting to see some useful applications. So on that relatively hopeful note, I will stop. Thank you very much.
So when you have to write your
Whether the weather is hot, whether the weather is not.
weather forecasting.
Okay. Yes.
So the time lag at which the skill of the numerical weather prediction forecasts exceeds that of empirical forecasts has been stuck at about something like, I don't know, 12, 14 days for a long time.
Right.
So, but you seem hopeful that that can be pushed out.
So,
So,
whoa, I didn't say that.
oh,
So there's a theoretical limit on how good weather prediction can ever be, right? Which is not that much further than 2 weeks, right? You could maybe make an argument for a month, but we're not there. What is possible right now? There's a lot of information that is not being assimilated into these weather forecast models, right? So there's a lot of information on effluents, right, that make a difference, even in the short term. There's a lot of information on small scale temperature measurements that are not being included. There's whole areas of the oceans where there's really not very much information that's going into these models at all, right? So can we improve how much data they assimilate? The answer is yes. There's a lot more data. Can you do that in a way that uses machine learning and artificial intelligence? I think the answer is yes. And you can learn weather forecasting from a weather forecast model. Right? So you might be aware of ForecastNet, which is an NVIDIA project, where they trained machine learning on 20 variables that came out of the ERA5 reanalysis. So you're using a model as truth, which is not quite right, but anyway. And they can match the skill in the weather forecasts out to about 5 to 7 days, right? But at a fraction of the cost in terms of what's going to be. So that allows you perhaps to do a lot more ensembles, to do a lot more of the tails of the distribution, but it doesn't, because you're using the current weather forecasting model as truth, you can't get better than the current weather forecasting model, right? So it isn't going to push out the predictability beyond 7-10 days as yet. But part of what Destiny is doing is that they're increasing the resolution of their the ECMWF weather forecasting model, and that will help, right? Currently that's running at about 9 kilometer resolution. They're hoping to do it at like 4 or 1 kilometer resolution. It will help, but it needs to be constrained by data. So you need to have orders of magnitude more data in order to do better with a higher resolution model. Yes.
Hey, so obviously you're talking mostly about models, and
Yes.
I totally agree with you that we can't use present day data to tune a model to do out of sample prediction because of the difference in the physics of what's happening. That everybody is agreeing on that. But you didn't talk about the use of ML for simply making some sense out of large satellite data sets. And as we go forward in the future where the models can't be a guide, right? Then we have to do something with this immense amounts of terabytes of data that we're pulling in. And I do think ML has applications there, and I wonder if you could speak to that.
Yeah, I mean, obviously, you see a large data set, somebody says, oh, let me try and find some patterns in those data sets. And the stuff that I have mostly seen is a kind of recapitulation of everything we've already learned, so somebody will do a.
Well, then you should come to our posters.
I will love to come to your so I don't need machine learning to tell me that ENSO is the biggest cause of variance in cloud. So I mean, I would like to see more data-driven improvements in understanding that might then inform what we do with these models. But my eyes and ears are open, but I haven't really seen a lot that would be great.
Come to our posters.
I will. Yes.
So you made a point that
I've been talking to the mic because there's people getting excited.
So you made a point that AI models are unlikely to supplant the physical simulation models for climate prediction in the future, which I welcome. I think there's a place for both. And then you talked about how the two could maybe strengthen each other or collaborate. But I'm wondering, one aspect that you did not mention is how AI might accelerate current, essentially even just PDE solvers, as opposed to replacing them, developing a kind of refined combination of the two technologies, where, for example, the solver just focuses on those parts of the domain which are most relevant for the prediction, but the prediction is the most sensitive one, and so on. Is there any word in there that you see potential for?
So there is potential there. And one of the examples where we're investigating that is the use of emulators for atmospheric chemistry composition. Right. So most of the models that you see don't have interactive composition. A few of them do, but it turns out that it's important that the ozone changes when the sun activity changes, or that ozone changes because of changes in circulation, or and you want to be able to capture that both in terms both for air quality issues, but also for the climate impacts of changes in aerosols and ozone. And so there is we have a lot of kind of box models that we can then apply, learn from all the different cases, and then just to use those to have an accelerated calculation of those things that we can then evaluate. I think there is one example of where you.
But that's again a bit more like just parameterizing some part of a model with
Right.
a machine learning model, rather than actually having a machine learning model part of the PDE solver itself, improving the quality of the PDE solver, like focusing on those parts of the domain which really are most of these fluid models, right? The model is much more sensitive to certain parts of the domain than other parts of the domain, for example.
Yeah, I mean, people have thought about that in terms of you concentrate the grids in places where you think something is happening that's important, and they've done that kind of in a mechanical way as opposed to a very machine learned way. But the problem with that approach is that it turns out that almost everywhere on the world is important. Right, you say, okay, well, I'm very focused on gravity waves that come from the interaction of the jet stream with the Rockies, but that has a global ramification. You can't do it for the Rockies if you're not doing it for the Andes or the Himalayas, right? So you kind of have to do it, and then the cost of doing lots of special things pretty much everywhere, it doesn't get you very far, because you'd have been much better off just increasing the resolution everywhere. But but we know how expensive that is. I mean, I could conceive of ways in which that could be better. I'm not hopeful that would actually work out very well.
Okay, let's thank Gavin for a great talk.
We are going to have a break in one moment, but Becca wanted to say a couple words before we did.
Right, thank you. And thanks for the awesome talks this morning. I really enjoyed them. I just want to take a brief moment to acknowledge Tom and Margot Pritzker, who are with us here right now, and the sponsors of this really exciting conference. So Tom and Margot, thank you both so much for your support for this conference.